pleasure today to have Zvonimir Dogic from Brandeis University. Zvonimir is sort of the scion of one of the most prestigious dynasties of condensed matter physicists in the country. He got his undergraduate and graduate degree from Brandeis, and then postdoc at Penn and ULIC. His grand advisor is Bob Meyer, who sort of brought soft condensed matter to this country. He invented liquid crystals that are used in all the displays you see now, in televisions and computers, things like that.
Who did, the grandfather?
Yeah, no, I'm not that old.
His advisor was Seth Braden, who's also well known to everybody in soft matter. I heard Bob Meyer talk about 5 years ago at a birthday celebration for someone else, and he gave a talk, and I said, Bob, this is great, you're retiring now, and this is the best work you've ever done. He said, it's not mine, it's Zvonimir's. So Zvonimir is going to tell us today about something that's even newer. His title is Autonomous Motility in Soft Active Matter.
Okay, so thanks a lot. It's very nice to be here and learn a lot about the research going on. And so, are there any undergraduates here or? So, okay, so this talk was prepared for undergraduates in mind, okay? And so if...
Good, then us faculty might be able to...
Okay, well, if undergraduates and faculty, graduate students know this stuff. Okay, so I guess I should, first say who are the people who did this work. And it all started with Tim Sanchez, who was really a great graduate student. He joined my lab. He came from a small school that didn't give grades and nobody would accept him. But so I was lucky that he came to Brandeis. He joined my lab. Within 6 months, he published a paper that I thought was pretty nice. And then he came into my office and said, well, I'm pretty unhappy with this. I want to do something really quite more challenging. And so I said, okay, I have a really challenging problem for you. And then for another 4 years, there was absolutely no results, right? And so I was really worried that I destroyed this guy's career. And then suddenly things started working, right? After in his 5th or 6th year of PhD, and he had a very successful PhD, and now he's doing a postdoc, and actually he's probably smarter, so he's starting a startup company right now. So that was followed by 2 other very good students, and some of the collaboration was done with this group of Andreas Bausch at the Technical University in Munich. Specifically, he has a very nice way of encapsulating things into vesicles that we use. Okay, so I want to start with the very basics. A long time ago, people came and formulated very simple models, and so this is one of such simple models. You have spins on a lattice, right? And so the spins want to be aligned in the same direction locally. And at low temperature, this kind of spins are, your energy is going to be favored, and the spins are going to align in a uniform state, and you'll get long range or quasi-long range order. If you increase the concentration, the thermal fluctuations start to matter more, and at some point entropy dominates, and you melt, this kind of long range order, this phase melts into an isotropic, high temperature disordered phase. And so what's interesting to me is that, people who proposed these models, I guess in 20s and 30s, I mean, how many PhD theses went into studying something like this? And it's really kind of, I don't know if they had any idea of how fruitful this would be, right? But the basic mechanism of how this phase transition takes place is well understood, right? You calculate the free energy of the system. It's energy minus temperature times entropy. And so you know if you're in this phase or this phase by just minimizing free energy, okay? And so we know how to do these calculations. Sometimes they are more difficult than other ways. But what we are interested in is what happens when these units, these particles, are actually far from equilibrium, right? So this is a system that's completely isolated. The units just fluctuate in accordance to laws of statistical mechanics, but you can cook up a lot of models which, in which this kind of spins are far from equilibrium. And so kind of a famous model that was proposed in 1995 was by Visek and his group in Hungary. And so it's a very simple model. I think, a decent undergraduate could, code this up within a few days, right? And so this is a non-equilibrium model, and this is a nice abstract. So somebody asked me, so I just decided to put the abstract. In our model, particles are driven with a constant absolute velocity, and each time step assuming the average direction of the motion of the particles in their neighborhood, and there's some random perturbation. We present numerical evidence that this model results in a kinetic phase transition from where these randomly moving spins have no net transport to a phase where there is spontaneous symmetry breaking and they all move in the same direction, okay? And so since these spins now, these particles, these arrows, move in the same direction, they move with a constant velocity, of course, they need to consume energy. And so what's happening is you have the spins, you have this probe spin, and it's moving with the velocity, and it changes direction, and how it changes direction depends on the number of neighbors.
So is the arrow the direction the spin is pointing? Or
yeah, the arrow is the direction the spin is pointing, and it's pointing with the same velocity, right? So let me show you a numerical simulation of this. Oops. Right, so you have these arrows, they're moving with certain velocity, and they change direction dependent on what direction their neighbors are pointing to. And so you start with something that's completely disordered, and for certain parameters, you get the state where all the particles point in the same direction. Okay, and so this is a state that has long-range order.
So they always move in the direction that they're pointing?
Yes, yes. But it's noisy, right? And so there's interesting transitions, and it really depends on the noise of this transition of first order or second order. And so the question is, what about experiments, right? And so, so the first type of people, the first things that people thought is perhaps, this is an appropriate experiment, right? Is you have a bunch of birds, these birds are flying, and the birds are just flying in the direction that the neighbors fly. And so, maybe this is something that this Visek model describes. But, doing experiments on something like this is, something that we, at least we don't want to do. And so we want to simplify the system. But there's actually people who do that, right? They put GPS on birds, and they track motion of the birds, and, and you can try to, make up something of this data. But birds, obviously, are more than just, calculators. They have complex brains, or simple brains. Okay, so the second, so you might try to simplify things. So you might say, okay, well, I take dilute E. coli bacteria, and this E. coli, just move, swim, and of course they can't be where its neighbors are. So when they collide, they might go in the same direction. And so if I increase the E. coli speed, you get the swarms, right? And so this is again a typical non-equilibrium pattern. And so, so you might get somewhere by studying the motility of this individual bacteria and trying to predict something that's, as complicated as this. But E. coli are also not a great, species, right? Their swimming velocity, I can't really tune it. The bacteria divide and die, and they need oxygen, they need food. 3D samples are very difficult to run for a long time, and so, but people do reasonable experiments with this kind of system. But I think the experiment that really kind of nailed this down is the following experiment. So this is the simplest experiment that shows this transition. So over here you have, these are motor proteins, and so these are proteins that literally walk along this filament, and this filament is extracted from your skeletal muscle. So when these filaments land on this bed of these motors, it's like, the kids who go to a rock concert and throw themselves onto a crowd, and then the crowd propels them forward. Okay, and this is all powered by ATP catalysis. And so what happens is these filaments are propelled at finite density, at low density, they're propelled at a finite velocity, and they just go in a certain direction. And sometimes they'll hit each other, and then they'll change their direction, okay? And sometimes they'll just pass through each other. But if you increase the concentration of these motors, you actually get this kind of flocking transition. And so this is really zoomed out now. You can't see individual filaments, but this is a flock of filaments that has about, hundreds of thousands of filaments. And so in a certain way, this really looks like a flock of birds, right? And so this shows that this transition in this non-equilibrium model is really, maybe real. And one could study it with this because now you've taken isolated components and they're fully tunable, right? So you can vary the parameters that are relevant. And so, this is something that you get by just taking two biochemical building blocks and putting them together in a certain way that you would like to, okay?
So when
yes?
you say there's a transition, what's the transition?
Okay, so at low density, all these filaments are going to move in random directions. If I increase the density of these motors, then you get this flock that literally has 10,000 filaments, and they're moving like a flock of birds.
Low density, they're completely independent of each other.
Yes. And then you get this flocking, okay? And so what I want to show you is that actually you can take these biochemical building blocks and you can put them together and you can get many, many different dynamical states. And so the challenge is how to, describe this from a theoretical perspective. Okay, so what are our building blocks, okay? So that's what we want to do. Explore from the bottom up the space of dynamical states that can be assembled with these biochemical energy-consuming building blocks, right? And so you can imagine that, nature actually takes these motor proteins and filaments and assembles a muscle, right? It assembles a mitotic spindle. It assembles a sperm cell, right? But if you start from the bottom up, these structures, these dynamical structures have been evolved, they evolved due to constraints of evolution. But you can imagine if you just put them together in a laboratory environment that you can assemble many more dynamical states than what you could observe in nature. And so I just want to demonstrate you the diversity of the states in this talk. Okay, so this is my outline. I'll tell you how, we have these building blocks, microtubules, and isotropic gels. And then I'll tell you something about how we assemble a completely artificial liquid crystal that's now called an active liquid crystals on a sphere. And then I'll tell you how planar active nematics are much, much more complicated than those that are on a sphere. Okay, and so what are our building blocks? Our main building block is microtubules. So these are just long filaments, and the way you get them is that you literally purify them from a cow, okay, from a cow brain. And so you have to go to a slaughterhouse, get a cow brain, and after spending 24 hours, you get about 100 milligrams of this protein. And that's actually what my students are hopefully doing right today. So,
Did you just order them? Didn't you order them?
it has to be fresh. So that's an essential ingredient. It has to be still warm when you kill the cow, okay? And so I had actually a student from NYU Kunta, and so he actually taped the whole process of how the cow was killed, and I didn't want to show that here. So,
So is each ball one protein?
this is each protein, and they polymerize into these long filaments. Okay, the other essential ingredient that we use is depleting polymers. So this is a depleting polymer, polyethylene glycol. And so what happens is if you have two of these microtubules, which I just represent as sticks, what happens is that this polymer cannot penetrate this yellow region, so the osmotic pressure on the outside is higher than the osmotic pressure on the inside, and you get a bundling of the filaments, okay? And so if you have filaments, they bundle in this configuration. They don't want to be perpendicular to one another. And you can directly observe this. Okay, so here you have a lot of polymer everywhere. You have these filaments, they're just moving around, and then they find each other, and this osmotic pressure drives them together, and you create this bundle. Okay? So that's just an effective, attractive interaction.
What's the bright spot?
This?
No,
That's even a shorter bundle, right? So this is a 3-filament bundle. So you'll see that this bundle, and so what's extremely important is that these filaments freely slide on each other. And so that's something that we're actually studying, is the friction between these filaments, and that changes, tuning this friction changes the behavior of the whole system. The third component that we use is molecular motor, and that's what drives the system out of equilibrium. This is a myosin, a kinesin molecular motor. It literally hydrolyzes ATP. It's a 10 nanometer machine, and it takes an 8 nanometer step. Every time it hydrolyzes ATP, it takes an 8 nanometer step.
Is there directionality?
Yes, it moves towards each end of microtubules are polar, and it moves to what's called one end of microtubule, which is the plus end. What we do is, this is our schematic of a kinesin, and it's labeled, and we make a multimotor cluster. So this is one kinesin, this is another kinesin, okay? And so what happens is, if you have a bundle with this kinesin moves towards the plus end, this kinesin moves towards the plus end, and this motor just moves towards the end, okay? At least in a PowerPoint simulation, okay? But we believe that's what actually happens in reality, right? So here you have a plus end, here you have a plus end. So this is a different polarity of microtubules. So this kinesin is going to walk here, this kinesin is going to walk here, and the microtubules will, this kind of happened fast. The microtubules slide past one another. The polymers don't slide, I just realized that the polymers don't slide past with the microtubules, maybe a little bit hydrodynamically, okay? And so if you have polar bundle, you get no polarity sorting. If you have apolar bundle, you get filament sliding, okay? And so what's also important is that if you have this bundle geometry, this motor walks for a micron, it falls off, but it probably rebinds to the filament very quickly. Okay, and so the processivity is greatly enhanced. And this is what you see, okay? You put these 3 components together, and you get bundles, and these bundles are just diffusing around. And now what I've done here is I've labeled both ends of a filament. And these bundles will diffuse around, but occasionally they'll encounter one another, and then you see they slid past one another, then this bundle rotated by 180 degrees, and then it stays static. So presumably what happens is these bundles come together in antipolar configuration, the motors push them apart, they rotate by 180 degrees, and then they rebind, and then they stay in this rebound state because now they're in the same polarity. Okay, we're actually trying to check that with a second harmonic generation microscopy. And so at low dilutions, you have isolated bundles, they're static, and that probably implies that they are locally sorted, polarity sorted. Bundle recombination reinitializes this polarity sorting. And so what we want to do is we just want to increase the concentration of these bundles so they more frequently find each other, and so they recombine. And
these motor proteins, the little things,
you don't see them. Yes, yeah, they're just floating around there everywhere, right? And so we increase the concentration by 10 times, and so this is what we see, okay? And so this was unexpected, right? Is you have
a concentration of what?
of the filaments.
Right.
And so you see that this solution that's initially a gel-like solution becomes completely unstable, and it forms this large-scale patterns, right? So this is 100 microns, and this develops into this kind of fully developed turbulent-like patterns, okay? This is very robust. I can zoom out, and so this is, really zoomed out, and so this is 1.5 micron, okay? And so this is, so these things run for multiple days, okay? And so what we have here is actually the same thing that you have in your muscle. You have, in your muscle, you hydrolyze ATP, you generate ADP, and then you have another biochemical circuit that takes that ADP and adds a phosphate to it. And so you have this regeneration of ATP that, when the sprinter runs 100 meters, it uses this ATP regeneration, and that keeps our system running for, up to 24 hours.
Is this essentially 2-dimensional or 3-dimensional?
This is 3-dimensional, but I will talk about 2-dimensional.
What's the time scale?
It's about, this is probably a 10-minute movie in everything, so I should put a time scale. So this movie is, tens of minutes, right? It's probably sped up 50 times or something. This is a very large piece of experimental crud, right? And so it's very useful because it's a brick. But this brick is actually moved by 100 microns, hundreds of microns, because it's advected by the flow that's spontaneously generated by this, swirling active gel that looks turbulent-like, right? But it's not turbulence because in real turbulence, you feed the energy at the microscopic length scales. Here, you feed the energy at the microscopic length scale.
So eventually you'll run out of ATP and then it will stop.
Yes. But that takes a few days, right? So it's not useful for any application, but it's good enough to take data. Okay, so I just want to tell you a few things about this gel. And so what is the microscopic dynamics? And so what happens is this is a useful, so here we really zoom in, okay? And so here we zoom in and we see individual filaments. So you have this filament and you can see how this filament bundles with each other. And that's what happens over here, right? So you can see how they bundle. And since they bundle, they might have opposite polarity. And this opposite polarity drives the filament extension. But now this is a percolating bundle, so it's anchored at its end. And so if I'm extending a bundle, but it's anchored at its end, then it buckles, right? So it's extending and buckling. And then once it buckles, the curvature increases so much that the filaments fracture. Okay, and so here you can see a fracture point. This is a time sequence. And so this is how the movie takes place, right? So here you can see bundles merge. As they merge, they break. They fracture, then this bundle merges with this bundle, and so you get this cascades of bundles merging, extending, buckling, breaking. So the whole system wants to polarity sort, but it never gets there. And so, are there any questions at this point?
So it actually breaks the chemical bond.
No, this is a very soft bundle. Each individual filament is 1 micron, and this buckling length scale is, so it's a composite bundle that's held together by these weak depletion forces. And so you're just fraying this composite bundle. The other thing that you can characterize is the effective transport in the system, right? So here you have 0 ATP concentration. These things just don't go very far. At highest ATP concentration, these are now tracer beads, okay? And these tracer beads are effectively transported by the system, right? And so the way you characterize that is you measure the mean square displacement as a function of time, right? So if you have a bead in a viscous solution, this bead, the mean square displacement is going to increase linearly as a function of time. And that's, this is a slope of 1, so this would be just a bead moving in a viscous solution. So at low ATP concentration, it's subdiffusive, which means that you have a viscoelastic system, and at high ATP concentration, these things are, essentially moving ballistically. Yes, the mean square displacement moves as t squared. That means that they are just moving essentially on straight lines. And so this shows you why this is nice, is because we can tune the system, right? We can tune the velocity from, and the transport of this gel all the way from subdiffusive to ballistic. If you have a bacteria, you're only sitting on one curve. Yes?
When you increase the consumption of ATP,
yes.
it just like speeds up the movie, or it also changes the correlation, like coherence?
No, it just speeds up the movie. So that's what I forgot to say, is that how much ATP you have determines how fast the motor walks. Okay? So you have enhanced transport and mixing. You can tune the mean square displacement, but on average, these particles are equally likely to go left or right. Okay? And so you don't go anywhere. And so this is something that I just thought I would show this because this was actually experiments that are done by Kuntavu, who was here. And so we took this active mixture and we put it in a geometry, right? And so this is a toroidal geometry. And so it's about 1 millimeter in diameter. And so you put this active mixture. We don't actually show gels. We just show these beads. And so when you put it in this toroidal geometry, what you get is spontaneous emergence of currents, right? And so this is literally, you can see that there is an effective current of these beads of flow in this direction, okay? And this is going to persist for hours, Okay, and so this is something that we really don't understand, right? Presumably, and that's a question, can you come up with some kind of effective hydrodynamic theory that would describe this transition, right? And so what the data indicates, but this is what we are working on right now, is if this tori diameter is small, this spins, and in this case, the spins indicate the position of the flow, it's completely random, right? And so if you put a bead, it's equally likely to go left or right. If we increase the tori diameter, then you undergo a transition to the state that's characterized by unidirectional flows. And so these things just spontaneously circulate for hours at a time. And so I think, I think studying something like this would be interesting because we have a lot of control, right? We know all the microscopic parameters, and we want to see whether we can describe this as some kind of non-equilibrium transition between two dynamical states. Yes?
Does that mean that if you can do simulations and predict the outcomes?
The question is, how do you coarse grain this thing, right? To do simulations on a microscopic scale would be too difficult because your building block is 1 micron and this is 1 millimeter. And so you really need to somehow coarse grain the system, right?
And you haven't done that, are you?
No. This is data that we took last month, okay?
Does it ever reverse if you leave it long enough?
No. Yes. Okay, so what I've shown you so far is I've talked to you about microtubule-based liquid active gels, right? And so you have this high-efficiency kinesin motors. We couple it with ATP regeneration. It powers this dynamics for a few days, okay? After 2 days, the proteins denature and your system goes, becomes, doesn't look so nice anymore. And so, you have this emergence of the spontaneous chaotic flows. And so in the future, and that's what we are doing right now, is studying the rheology of these things and emergence of directional currents. But what I really want to talk to you about is active nematics. And so, this looks like something that's inside a cell. And so what we do is we put this stuff into a lipid vesicle. So this is just a bag, and we put this active mixture into a lipid vesicle. And this is what you get. Okay, and so I'll explain to you what you get later, but what you get is that all these bundles go to the surface of a lipid bilayer, right? And so I'll show you that later, right? And so you get this dense layer of microtubule bundles that's shown over here, okay? And so they form a thin cortex, and they're all aligned. And this is an example of a liquid crystal, okay? And so
It can't be all aligned if they're
on a sphere.
The surface of a sphere.
Yes, exactly. I'll get there. Okay, locally they're aligned. So just for people who don't know, is if I have rod-like molecules like my microtubules, if they are in dilute phase, they'll be just randomly oriented, and this is a completely disordered phase with short-range positional and orientational order. If I increase the concentration, I go to a transition that has, so this is another example of a phase transition, but what's different about this phase is that there's no arrows. So the rods, they're equally likely to point up or down, so this has to be described by the, quadrupolar order parameter, but you go to this phase where all the rods are pointing along the same direction, and this is a long-range order, right? But if you look at the center of mass of each of these rods, that would be a short-range positional order. And so that's an example that's been studied for a very long time. And so, this is very important, right? Rods are equally likely to point up or down. So you get what's called a nematic order. Now, as you properly said, I have these lines and I want to cover a surface of a sphere with them. And that's when I get in trouble, right? And you know that you get in trouble, from your everyday life, right? So this is the surface of the Earth, and you want to cover it with parallel lines. And you can't do that, right? You need to have two equators, right? A North Pole and a South Pole, right? And so if I sit on the North Pole, it doesn't make you can't ask a question where is north if you're sitting on the North Pole. So this is mathematically a singularity, I guess. Okay. Are there any questions about this? So this is the same, this could describe my liquid crystalline director, right? So this tells me that you need to have these defects. There's other examples from other venues of life. So, you can have, your hair, and so that's also a nematic field, right? And so, if you have your hair, and if it's not sticking perfectly perpendicular to your head, then you have an in-plane director, and, I guess depending on the boundary conditions here, you must have this kind of topological singularity here, right? And so, so, you can try to calm your hair, but mathematics says that it's a futile job.
Baby's mother that
yes.
has a topological singularity.
Yeah, okay, yeah, that sounds scary. Although I guess Dave has like a half-class defect that just propagates and then a line. So one part of your defect escapes to the. Okay, but so there's another type of topological singularity that's actually more important for our case, and that's shown if you zoom in and if you look at your finger, right? So your finger also has these parallel ridges, and then you have this topological singularities over here and over here. But this is a slightly different topological singularity, right? If I sit on the North Pole, I rotate 360 degrees. If I sit at this topological singularity, I just rotate 180 degrees. And there was actually, a father of a famous physicist wrote a paper about this. Okay, and so this is Professor Lionel Penrose, who was a father of Roger Penrose, who most physicists know about, and he wrote this paper called dermatoglyphic topology, right? And so he identifies the basic defects of that you encounter on your skin, and so this is a loop pattern and this is a triradius, right? And so you can have a digit here that's has no topological singularities, but here you can have a digit like this, and you can always see that here you have a topological singularity of one kind, and it has to be followed by another kind, right? So they always come in pairs, and here you have two of these triradiers, and they're followed by two loop patterns. And so you can formulate topology of this hand, and so this is essentially the same physics of liquid crystalline defects, right? And so we have a way of talking about these defects, and so so this is a North Pole, right? And this is the lines of longitude, right? And so if I go around the North Pole and I have my test rod, I go around and I rotate this rod by 360 degrees. So this is a topological charge of +1. But that's actually not what we see in liquid crystals. Most of the time we see topological defects of charge 1/2, right? And so these are your loops and triradias in the language of Lionel Penrose. If I rotate this, I only rotate this rod by 180 degrees. So this has a charge of +1/2, this has a charge of -1/2. If you have a polar symmetry, you can have these defects, but that's maybe a slightly technical point. And so I have a defect, I want to tile a disk like this, I line it up, and so I have to have this topological charge of +1, I can deform it, I can bring another hemisphere, and so I have these two defects, and the total topological charge on a sphere covered with a nematic has to be equal to +2. So that's just the law of mathematics, actually. But the law of mathematics also says that I can take a charge of topological charge of +1, and I can just literally split it into two and get two defects of charge +1/2. And that's actually what happens on a liquid crystal. Right? If you have a liquid crystal, you could have something like this that's a surface of the Earth, which has 2 +1 defects, but that's energetically unstable, and you lower the free energy by splitting this +1/2 defect into 4 +1/2 defects. And these defects repel each other, and they sit at the corners of tetrahedra because they want to be as far apart from each other as possible.
So how do defects, when you go from the Q equals 1 to 2, Q equals 1/2,
yeah.
You're somehow doing that in a continuous fashion?
You can continuously do that.
Other, right?
Yes. A liquid crystal doesn't do that. But topologically, I'm not breaking any lines, right? This is a continuous deformation.
Right. It's continuous going from there to there.
Yes.
As opposed to other things that wouldn't be continuous.
Yes.
That are
Yes.
interesting.
Well, I can't just plop up another charge of +1, right?
Yes.
That requires me to rewire the lines, I think. And so, and so this has been verified experimentally. And so this is our sphere, right? So this is our nematic sphere. There's 4 defects sitting at the corners, right? But our sphere with our defects is different because our defects move, okay? And so they have a finite mobility. And so you can see here that they're moving on the surface and they have a finite mobility. So the elastic forces want to keep them as far apart from each other, but here, if I have a tetrahedra inscribed on a sphere, I can't move all the points with a constant velocity, right? And so the system is inherently unstable. And so the question is, what does it do, right? What kind of dynamical pattern it does?
Are the defects single points on this?
Defects are right. This is a defect, this is a defect, and so I can just take a bunch of movies and I can track these defects, right? So here's one defect, here's another defect, here's another defect. There's 4 + 1/2 defects, and I just track them as a function of time, right? And so this is just my reconstruction. And the question is, are these patterns completely chaotic or are they something else, right?
And you never see the formation of a triradius in a loop?
Not for this geometry.
And is it true that there are forces that are elongating the spheres? They're being squeezed?
I mean, there is forces. I mean, this is a vesicle with a very tense surface tension, and so the forces generated by this active nematic cortex are not enough to distort the liquid crystal. But I'll show you that later. Okay, so the way we describe this is, let's say I have a tetrahedra. I have 6 angles. I have 4D. I can describe the configuration by 6 angles, right? So this is a center of a loop. This is a defect 1. This is a defect 2. Alpha 2, 3 is 109, as is everything else. And so I have another configuration that I choose, and here alpha 1, 2 is this angle, it's 90 degrees, alpha 1, 3 is 180 degrees. And so I have the trajectories of these things, and I just follow them as a function of time. Here I plot all the alphas, and here I plot the average of alpha, and you can see that this thing nicely oscillates between 2 states. One state has an average angle of 109, so that's a tetrahedral state, and the other state where it wants to go and it passes through is this planar state, right? In this planar state, the average angle is 119 or 120. And so you can see here that any given point, 2 angles light up and they become almost 180 degrees, right? And so the system oscillates between 2 states. It oscillates between a planar state and a tetrahedral state. And so I can tune this oscillations by tuning.
Planar state being then 90 degrees?
In a planar state, I mean, I have 6 angles, right? In a planar state, 4 angles are 90 degrees and 2 angles are 180 degrees, right? And so if I look at this graph over here, I can see that like 2 of these angles light up, and that actually corresponds to close to 180 degrees. And then at another point, other angles light up, and then 2 other angles light up, and so on. Okay. Okay, so now as Jasna said, these are vesicles, they are floppy surfaces, and so I can make them floppy. And so here you can see that these defects actually, this motility of these defects couples to the deformation of the vesicle, right? And so I can do that even to a more extreme case. And so what we do in this movie is we just add a lot of sugar to it, right? And what makes sugar makes the osmotic pressure on the outside higher than on the inside. The water flows out, and that makes the vesicle very floppy. And so you have this vesicle, it's initially planar, and then as I suck the water out of it, it's like deflating a balloon. Then you grow 4 of these defects, okay? And so it grows 4 arms, right? And at any point, it only grows 4 arms, right? And so here you have 1, 2, 3, 4, right? And so these arms are moving around. And so, if I show you something like this, you say, well, this is something that you find in a pond, in New York City sewers. But it's actually just a material, right? There's 4 components here, right? So it's something very simple. And so what we want to do right now is we want to put this into a gel, an open gel, and see whether this thing can start crawling and, you know, invading people and now curing disease. Sorry, that's a proper.
So what happens when you get? Is this like a whole bunch of these things line up?
Well, I mean, this thing generates force, and then it just pushes outside and generates one of these arms, right?
Is that one a whole bunch of lining up next
Yes,
to each other?
yes. I mean, you can see here, right? You have this defect, and you can see how this defect is locally deforming the vesicle surface.
Right. Yes.
Are
Yes.
all the microtubules on this surface?
Hmm?
Are all the microtubules?
Yes,
on this
yes.
surface?
If I focus, yeah, they are all pushed on the surface because the system is extensile, and so all the microtubules are on the surface, and they always push outside, right? If I want to go back inside, I have to contract. And if I contract, I don't contract. The system is always pushing outward. And so these are, you know, you can do 3D reconstructions of these animals. And so, you know, so this is what you can grow in the lab.
They never break apart?
They do. I mean, these are, you know, these lipid vesicles are wimpy, right? So we
The forces that are responsible
Yeah.
for these weird shapes also can split.
yes, that's the forces, they break them. And so we want to use things like polymer vesicles because then these things can live for multiple days, right? Okay, so what I've showed you so far is, you know, active nematics of a sphere. So I've told you a little bit about the topology. The topology determines the defect number. You know, we've studied defects in normal condensed matter. They're always these passive objects, but defects in active nematics acquire motility, and when you confine them on a surface, they exhibit this deterministic oscillatory dynamics. And what's really important is these defects in this configuration live forever, right? And so that's a nice thing. And so now I'll show you a planar active nematic. That means I take this nematic and I just put it on a planar surface, and I'll show you that things get much more complicated and hairy, right?
They live forever because of the topology.
Yes.
It forces them to.
Yes. Which makes that actually simple because it's completely different from normal liquid crystals, because normal liquid crystals, when I have a LCD display that Dave Pine is using right now, you know, I mean, then I can create a uniform state that's defect-free, right? And so normal liquid crystals, if I put them on a sphere, it's more complicated than a planar case. But in active nematics it's different because I'll show you what happens in a planar case, okay?
That's why we don't have spherical monitors on it, LCD monitors on it.
Yeah, because you would have, yeah, I mean, for a variety of reasons, but one is you would have these defects and, you know, yeah. Okay, so we can make this two-dimensional active liquid crystal on a planar surface by creating an oil covered with a surfactant and then water on top, okay? And this osmotic forces that push these microtubules together also push the microtubules onto the oil-water interface. And this is what you get, right? This is your active nematic. This is my tri-radius and my loop, right? Or disclinations of +1/2 and -1/2. And so these are my topological defects, okay? And so this is a movie of what an active nematic liquid crystal is. And the challenge in the field is to really explain this, right? And so this is much more complicated, and I'll try to explain you what's going on here, right? So here I have one defect, I have another defect. Here I have two defects that are actually annihilating with one another. Here this defect might annihilate with this defect. Actually, no, they missed each other, so they go their own separate ways. And so we need to wait for defect creation. And so where does that happen, right? So here you have two defects, but they come at a wrong. So here you see you create this bend, and you created a +1/2 defect and a -1/2 defect. This defect merges with this. And so you can just see that this is a very complicated dynamics. So, okay, so here you nicely see how you get this bend breaks, and you create a defect here, and you create a defect here. So that's how you create a defect, right? So in this state, you're continuously creating defects and annihilating defects. Here is another process of defect creation. And so then this defect might encounter this defect, and so this thing goes on, right? And so it's very complicated dynamics. You have a nematic liquid crystalline orientation that couples to the flows and things like that. And so what are the two basic processes at play, right? Is you have this bend instability. So, okay, so if I have a normal material, I bend it, it wants to become straight, okay? It wants to bend back and become straight. Here, if I bend this material, it actually wants to bend more, right? And so as it bends more, so it's inherently unstable. The liquid crystal, even if I prepared a perfectly uniform state, it becomes, you have a small fluctuation in bend, and this fluctuation grows in amplitude, and eventually, this curvature becomes so large that you fracture the sample and you create two defects, right? And then these defects anneal, but the +1/2 defects moves away, right? And then the other process, if I were just creating defects, it would be a mess. And so I have this process of defect annihilation, where if they come at the right angle, they can come together and you create a uniform state. Yes?
When you say it starts bending and wants to bend more,
yes.
That means that the creation of these defects is energetically favorable, or not?
Yeah, I mean, you're always creating them, right?
But is it because it's active, or just...
Because it's active, yes, because you have these extensile stresses. No, because of this active stresses, because this active stresses now push in this direction, and they drive this instability to higher amplitudes.
So then you would just get more and more defects over time. But now,
but you also create defects, but then you also, at some point, once you reach high enough density, they annihilate with one another.
It reaches some equilibrium.
Yeah, so the steady state, it's not equilibrium, but it's a steady state in which the defect creation and annihilation are balanced, right? And so, people talk about an active nematic, but the actually active nematics do not exist, right? Because if I prepare an active nematic, means a phase with a long-range orientational order, right? But you can see here that if I prepare something that has a long-range order, it becomes unstable, and you create this instability, right? And so that was the thought in the field, right? Is active nematics, people talk about it, but you actually can't create one because it's unstable. And so you can create large areas of these active nematic liquid crystals, and so you can track these defects, right? And so you have a -1/2 defects, that's this blue lines. You have red lines that are +1/2 defects. They move around, they annihilate with one another, as is shown over, so or sometimes they go out of the screen, so there's there's a lot of information in this kind of movies, right, and that you track, right? And so perhaps it's easier if I remove the background, right? So now I'm just showing you defects, right? And so these are defects, these are -1/2, these are +1/2, they'll annihilate. The tracking is not perfect, but we believe it's good enough, right? As you can see, these +1/2 defects essentially move along straight lines, and that's shown over here. And so this is the dynamics, right? And so what happened is the student actually, at some point produced movies like this, right? And so if you look at here, this is +1/2 defect, and this +1/2 defect has an arrow, right? I can assign an arrow, it has an asymmetry. If I look at this picture, if you look, all of these +1/2 defects, actually a vast majority of them point in this direction, right? And so if I have arrows, there's nothing that doesn't tell me that these arrows can align with one another, right? And create a active nematic liquid crystals of motile defects. And so if I plot the orientational distribution of these arrows, you can see that it's anisotropic, right? If it's isotropic, this would be completely flat, but you can see that these arrows have a distribution that's anisotropic, and so they're equally likely to point in this direction and in this direction. And so this is a nematic order, right? They could also, in principle, create a state in which they are all in polar order. So defects are equally likely to point up or down, so that's this nematic symmetry. And so what I can do is I can measure this probability, the angle of this probability distribution function, and this is where, you know, our system is nice. I monitor this angle, there's some noise with it, but I monitor it over 9 hours, right? And this angle stays flat, right? And so I say, okay, well, this is pretty good. So, you know, this angle is flat, so this is a liquid crystal with a long-range order, but let's see how it persists in space. And so, you know, since it takes 9 hours, you know, so what we can do is we can measure the average orientation of defects in this screen, right? And then we move to this screen and measure it and move to this screen. And so this arrow, the magnitude of the arrow tells me what is the magnitude of the orientation. The orientation of the arrow tells me what is its orientation, right? And you can see that this persists over centimeters, right? The defect spacing is about 50 microns. So this is, you know, 100 defect spacing. And so I said, okay, to my student, okay, this is pretty good. Let's go to larger spaces, right? And so we went to 6, you know, so this is, you know, a 6 centimeter sample, right? And so you can see these defects, you know, propagate over, you know, this defect orientation propagates over samples on 10 centimeter scale, right?
So those divisions into the small squares are just arbitrary.
Yeah, because I can't take a movie of 6 centimeters with a micron resolution, right?
Yeah.
So I analyze this, but I know that the orientation doesn't change over 9 hours, right? And so I just can scan this, right? And it takes, you know, I don't know, a few minutes to scan the entire field. And so, you know, I mean, you know, if I was really, you know, mean advisor, I would say to my students, well, let's make a 60 centimeter sample, but I don't know, you know, what that would teach us, right? Because, I mean, it seems that this order persists, it persists for a very long time, right? But whether it's a real true long-range order or a quasi-long-range order, that those things are hard.
Is it a rectangle?
It's a rectangle, right? So you would say, well, this is just boundary conditions, right? And so we also did this experiment, right? This is a spherical geometry, and so, you know, and so here you have these defects, and so you can see that more or less it ignores the boundaries. So the anchoring at the walls is very weak.
Is it spherical or circular?
Circular, sorry. I mean, I always confuse a sphere and a circle, right? But it's... And this difference is actually because the density changes, right? So here, and I'll explain that in a second. So we believe that this is not some kind of boundary-induced phase, but this is a phase that's a bulk phase of this active nematic liquid crystals. And so, you know, so you have this kind of funny phase in which defects are created. They last on average about 10 seconds, and yet the order propagates for multiple hours, right? And
is the defect direction correlated with the director direction?
yes. So defect, this is the orientation of a defect as a function of its lifetime, right? And so this is a defect orientation at low ATP concentration. So defects last a long time, right, before they encounter the oppositely charged partner, and they're born with certain orientation, and they die with a certain orientation, right? And so all of these defects keep the orientation throughout their lifetime. And so, you know, so what we are working on now is actually trying to find an order parameter to see whether we can actually melt this phase of defects into an isotropic phase. And so what we are changing here is the retardance of this nematic field, which tells you what is the thickness of this nematic field. And you can see that the order parameter of this defect, active nematic defect, is very high for very thin films. But then as we increase the film thickness, it drops down. And the question is whether it goes all the way to 0 or whether it saturates at a low but finite order parameter. We don't know that yet.
So you're going from like two-dimensional system to a three-dimensional
Yeah, but it's really, I mean, both of these systems are pretty two-dimensional. It's whether it's a monolayer or 5 layers, right? So we don't understand this, but this data seems robust. Okay, so what I started with, I told you about this classical phase transitions that people have studied for a very long time of the spins. And so right now we have this a very different phase in which the spins are associated with these defects. These defects are motile, they annihilate, they are created, and so the challenge is to describe it. And I don't know if it's even sufficient to just look at the defects. Maybe one needs to look at the entire field, the nematic liquid crystalline field. And so, so you have this bend instability that locally destroys nematic order and generates defects, right? Yet on larger scales, this anisotropic defects interact with one another and recover long-range order, right? And so the active nematics actually do have long or quasi-long range order, okay? And so this brings me essentially to the end of my talk, so I'm not going to say anything about this, but what I'll say is we started with some very, very simple building blocks, right? Is microtubules and clusters of kinesin motors. And actually, Stan Leibler and Francois Nedelec did some very nice experiments a long time ago where they've taken these two components and they made asters of them. And once you confine asters into circles, you can change these asters into vortices. And so this was an interesting work. We've just added one component to it, a depleting agent. And this depleting agent led to the formation of these isotropic gels. And if you increase the microtubule concentration, these isotropic gels transitioned into dense nematic liquid crystals. Now, what I haven't told you about is you can take these bundles and you can attach them at their base. And these bundles, which are extensile, are actually going to start spontaneously beating left and right. So this is an example of something that actually might have a biological relevance. This is a tail of a sperm, right? So this is, but the tail of a sperm has 650 components, right? This has 4 components, and the functionality is the same. And so, so when I saw this, I was really excited because I thought, well, this is great. Now I can write a NIH proposal and I'll be rich from now on. And so then I got a dose of reality because biologists came back to me and said, well, everybody knows that sperm is driven by by dinins, and the PI is using kinesin, and so therefore this can have absolutely no relevance to, to any biology. And so I said, well, I better stick with physics after that. If you increase the density of the sperm tails, they'll actually synchronize and create this, metachronal waves that can transport things along. And then if you can confine it into the spheres, if you change the osmotic stress, it leads to shape changes. And then if you have one of these particles and you provide adhesion, this adhesion actually drives the motility of this droplet, right? And so this is just one example of how you can take these very simple components and start putting them together, and you get this dynamical phase space, right? And so far we are really kind of just stumbling along and discovering interesting things. And so the challenge is really to develop some kind of theoretical models that can help guide our wandering around this interesting phase space, right? And so hopefully these experiments will motivate those kind of developments. So with that, I'd like to thank you very much for your attention, and I'll be happy to take any questions.
Are there questions? Yes.
On the 2D nematic crystals, you
Yeah.
get a lot of defects.
Yes.
But they're also a lot larger, right? You're looking at scales for millimeters.
Yes.
20 microns.
50 microns or so, yes.
Right.
Yes.
Do you look at larger spheres?
We want to do that. But yes, so the spheres don't generate additional defects because you have this bend instability, and there is a certain length scale associated with this bend instability, and the spheres are below this length scale. And additionally, you have a curvature that suppresses this, generation of defects. So I believe if you increase the size of these things, at some point you'll start generating additional defects. That's very hard. It's very hard to make 100 micron vesicles. So we want to do that with emulsion droplets. But emulsion droplets, we need to index match it, and there's issues associated with that. So it's never easy, right? But I've been That's why we do those things. And so,
For the motile droplet, you can see it like moving a lot.
yes,
Do you see that the motion is related to the stuff on the surface?
yes, yes.
Do you have any idea? Because like, it's a lot of them on average, because of the state variable, on average it should be 0.
Yeah, on average, these things actually, if you analyze the MSD of these things, it actually behaves like a Brownian. This is a 100 micron emulsion droplet. It behaves like a Brownian particle. On short time scales, it moves ballistically. On long time scales, it moves diffusively. And the transition from a ballistic to diffusing motion is determined by how long does it take for a defect to move between the opposite poles of the defect, right? So you have this defect, it provides a kick, the droplet moves in a certain direction, and then another kick defect comes, the droplet moves in the other direction. So it's not going anywhere, right? It's just moving. But, so what we're trying to do with that is we're trying to, make a crystal of these things. So this would be like a colloidal crystal of 100 micron particles that have artificial Brownian motion, right? But that also has its challenges, like drift and...
Does this work, the cilia work with dining instead of quiescent so that you become rich?
Rich? Yes, yes.
You're using the wrong protein.
Huh?
You change your motor proteins and
Yeah, I know, but it took Tim 4 years to purify kinesin, right? So I need to find a poor soul who's willing to suffer through a lot of biochemistry to purify another protein, right? So these things are not easy for us. And so, we want to do that. Actually, dynein is minus end related and kinesin is plus directed. And so you could imagine that a combination, you could imagine increasing the complexity of your building blocks by a lot. And so.
Also, are your nematogens, can you control them with magnetic field?
These things are, I'm sure that these things are nanonewton forces or even larger. And so we actually tried with the guy at Johns Hopkins, what's his name? The liquid crystal guy. Sorry, I should know this. Lahini, yes. So he has these nice rods that are magnetic rods, right? And so I think that with that we might be able to, if you dope this liquid crystal with a real magnetic nickel rod, we might be able to, influence it with external field, and then we could be able maybe suppress the instability and see interesting things.